Okay, turning to the top of page 26, which is the last page in the organic unit, we want to look at some organic reactions. And again, there's a lot of detail here at first that might overwhelm you, but remember the questions on this aspect of the unit, or this part of the unit, are really on a matching level, so don't be afraid. All right. So the first thing is combustion, and as a friend of mine used to always say, combustion is about burn, baby, burn. Disco Inferno. You disco maniacs out there. That'd be way past your time. Anyway, for combustion, the reason why we say burn, baby, burn, because combustion is just a fancy way of saying burning. And if you turn your attention to the top of table I, you'll see that I cut and pasted 4 examples of combustion. So for combustion, you're going to need something organic. And then with some oxygen. And then in each case, you're going to produce carbon dioxide and water in every single case. So here's your oxygen. And then carbon dioxide and water. So these are all examples of combustion reactions. I guess I would focus on the carbon dioxide and water to distinguish combustion from the other types of organic reactions. All right, now let's look at the other examples. And again, this is going to be on a matching level, so don't sweat this. Now let's look at substitution versus addition. So that would be organic reaction types 2 and 3, if you want to put numbers on this. And we're talking here about the substitution of hydrogen with halogen. And remember, your halogens are with FClBr or I. All right, so it's a substitution with halogen. And here's a nice example of that, where you have an alkane, and only alkanes undergo substitution. And here's an alkane, and here's a hydrogen atom that's going to be substituted by this Cl2. So maybe we should draw the CO2 to make it more clear. And so one of these chlorines ends up substituting this hydrogen here. What happens is it attacks that bond, that single bond there. It substitutes the hydrogen. And the hydrogen that gets kicked out ends up pairing with the other chlorine. So you'll notice you'll get 2 products with substitution, compared to addition, which will give you 1 product. We'll cover that in a second. All right. If you want to write this out, it would be C2H6 plus Cl2 gives you C2H5. There's the hydrogen that got kicked out. A Cl substituted it, plus HCl. And then for addition, you're talking about either alkenes or alkynes, either double or triple bonds opening up to this. All right, so only alkenes and alkynes do this. And what's happening here, we're talking about the addition here of halogen or hydrogen. Of halogen or H2, hydrogen. And so let's show you how that works. So here's a double bond in an ethene molecule. And the Cl2 in this case here, remember it's a Cl2 attacks the double bond instead of the single bond, because the double bond has twice the amount of electrons, and the chlorine, being electron hungry, opens that bond up. So here's that double bond, and it opens up, and you end up attaching one chlorine to each carbon, as you see here. And so it's called an addition because you're just adding them together to do so. So in the formula, it would be C2H4, that you can tell is an alkene, H2H, CDNH to 2N. And then here's plus chlorine. Now you just add them together, and you get C2H4 Cl2. So here you get one product, while in case of addition you were getting two products. So we have substitution, addition, and the first one was combustion. All right, let me erase this here. We'll look at the other reactions. They really are not hard at all. Of course, there are many more organic reactions that you'll learn about in some other course. Organic chemistry could really be a killer on the college level, but here's just an introduction. Now let's look at fermentation. Of course, we're talking about the fermentation of sugar here. That would be reaction type number 4, and then 5, esterification. So the fermentation of sugar by yeast. And glucose, you'll probably recognize there's your sugar. And what happens is you end up producing alcohol, which is a drinkable alcohol, ethanol, and carbon dioxide. All right, so I guess I would remember here above all the glucose as a distinguishing feature of this reaction. And then an easy way to remember this is that little cartoon to this. So fermentation is when you take grapes and they turn into the active ingredient in vino, wine. And the bubbling, the natural carbonation of champagne, right, is due to the carbon dioxide which is produced. All right, so that might help you to remember that. And then esterification is making an ester by dehydration. Some people might call this a dehydration synthesis. Dehydration, of course, is the loss of water. See if I get a better marker here for you. Point this out. So what you need for esterification, you're going to need an acid, which is what we have here, ethanoic acid, and an alcohol, and you heat the both of them up. What happens is you end up losing water in between them. Oh, that's a better marker. And here's the water that's lost upon dehydration, and then the remainder, the two pieces that remain, lock together and form the ester. And here's the ester functional group, the ester linkage. So esterification of an acid and an alcohol react to produce, an acid and alcohol react to produce water and an ester. Let's write this up here in formula. So it's CH3 COOH plus, now I'm going to write the alcohol backwards, HO CH2CH3, and then we'll end up producing water, of course, which breaks off from these two. That would be this here. And then the ester, which is CH3 COO CH2 CH3. I do that just so you could recognize, again, how to see the ester linkage in a line formula as opposed to a structural formula. All right, we'll see some examples of that in the questions also. or in the extended unit. I sound like a commercial for the extended unit, but I'm really proud of it. It will help you. A number of students have given me a lot of students have given me positive feedback on that. Get this spot right here. And then continuing with our coverage of reactions. So that was reaction number 5. Saponification is a monster reaction. It looks like it at first. It's really not that hard. Saponification is making soap. Lower this down a little bit so I can reach it. So we're talking about making soap the old-fashioned way from fat. So you're going to need some kind of fat to do so, which is what this is here, this big fat molecule. And you're going to need some alkali or some strong base. So when you boil the fat in sodium hydroxide, remember that it's mostly almost 100% ionized. What happens is the hydroxyl groups come in here and they end up ripping this chain here, as I have it depicted here for you in your notes. End up ripping this chain here. And then this piece combines with the this piece here combines with the OHs to give you this here, which is a glycerol molecule, which is a good way to distinguish this reaction from the others because you're producing glycerol. And then these pieces here of the fat molecule, which were tied to this backbone since the OH came in and hydrolyzed it, broke this bond, better said, because you don't need to know that term. Then these 3 pieces are no longer united. You have here the salts of these pieces, the salt of actually the acids that originally this came from. So I think of soap as a salt of acid product. In fact, if you put in a hydrogen here, you would see the COOH. So the salt of an acid product. All right, and really this is a matching one, and the distinguishing feature would be that glycerol that's made. And so that's saponification. And then for the next reaction, which is polymerization, you'll see the 2 types of polymerization. Let's look at that. A polymer is a long chain molecule. Maybe we should start with just that here at the bottom. All right, it's a long chain molecule consisting of many molecules of the same thing over and over again called monomers. So if this represents molecules, these beads here, if we join them together, whatever these beads represent, different molecules, and I'll give you examples in a second, then all together, all of these monomers put together would give you a polymer, which means many monomers, poly more than one. All right, and there are 2 ways to link up these monomers. One is going to be through an addition that's gone wild, and the other one through a dehydration synthesis. So let's look at that, and let's try the addition example. So in this case here, we have, in this example, in addition polymerization, what we're adding together here, the monomer units, let me just lower this so we don't see the condensation. The monomer units would be these right here. These are the beads in the chain that we're adding together. And so they add together when you pressurize, when you bring these molecules together and you add a catalyst, and the catalyst ends up removing a hydrogen or hydrogens, which make them link together and give you this monomer. this happens to be, it's not very clear, I'm sorry. But you'll see this in one of the questions that I chose in the back, how many single ethynes, which these are ethynes, end up giving you a polyethylene or polyethene. All right, so now let me just elaborate on this. So let's put these down here to make it easier to see what's going on. So let's draw 3 ethene molecules. And now that's separate monomers. And now to link them up, what happens is that the catalyst removes hydrogen. And so now this carbon here, which initially had 4 bonds, now has only 3 bonds. And so it's looking for that third bond, so it ends up adding on to this carbon, which breaks that bond. And now you have 2 ethenes together. And then this carbon again is unhappy. And so it adds to this carbon, which breaks that bond, and so on and so on and so on. And we end up forming one long chain of ethenes united to each other, so we form polyethene. Technically it's called polyethylene. All right, so as far as examples, other examples with plastics and rubbers of addition polymerization. Plastics, rubbers, these are all ways of forming addition polymers. You probably have heard of PVC pipe, a lot of backyard furniture is made out of PVC fences, polyvinyl chloride, and then there's also polyethylene, as we just said, polystyrene. These are all examples of plastics that are made through addition. And then the other way to link up monomers to form a polymer is through a dehydration. There's a friend of mine puts it, a dehydration synthesis that's gone wild, because wherever you can lose water between these monomers, you do so, and they end up linking up over and over again. So let me show you that with a condensation polymerization. All right, here you have 2 amino acids linking up to each other, glycine and alanine. And so condensation is, polymerization is the forming of a polymer. These monomers stick together through the loss of water. So we end up losing water here. So they unite, as you can see here, loss of water. And because they still have 2 ends from which you could end up losing water on and on again, provided there's other amino acids here, we end up with a chain of amino acids. Each time there's a loss of water, an amino acid is added to the chain. So think of a protein as an amino acid polymer. Amino acid 4, etc. So a protein, also known as polypeptides, because they're polymers of amino acids. And then, of course, other examples would be carbohydrates. Carbohydrates or sugars are polysaccharides of glucose, where they're polymers of glucose. Again, that are united through the loss of water. So they're known as polysaccharides because they're polymers of glucose. I'm not sure, I might do a spell check on that. I'm not sure if there's 2 C's in polysaccharides. Anyway, other examples you might note, as I have there in the notes, cotton, polyester, natural fibers. For cotton, polyester is a man-made fiber, but polyester, again, it's a esterification reaction, continual loss of water. No, that's not a natural. It is done through the addition process. So polyester. And I probably misspelled that too. There's no H in ester. My spelling has gone down the tubes lately. All right? So here we have examples of condensation polymerization, proteins, carbohydrates, some fibers with that. And the big thing you need to note is it's a dehydration synthesis. But although I'm limiting it here in this example to 2 amino acids, to have 3, 4, 5 amino acids, I think of it as a dehydration synthesis that's gone wild in the sense that you could lose water everywhere to link up these monomers. Okay, I think that's good coverage for the organic reactions, and it's really to end this unit here. All right, so you can go to the questions if you like on organic chemistry. There's a lot of questions that I have in this review for you, or you can go to the extended review if I haven't said that enough times. It's got to be real annoying by now.